Welcome again, ladies and gents, to another flipped lesson. Today our focus is going to be understanding what the difference is between a polar and a nonpolar covalent bond. So we've defined this word covalent already in class as electrons that are shared in a bond between two atoms. So this is for nonmetals only. So for example here, H2 are both nonmetals, so they make a covalent bond, and HF are both nonmetals, they also make a covalent bond. So what's the difference between a nonpolar covalent bond and a polar covalent bond? Up until this point, we haven't really talked about how electrons are shared between the atoms. So if you are a nonpolar covalent bond, that means your electrons are equally shared between the atoms in the covalent bond, which I'm sure you've already guessed means polar covalent bonds are going to be when electrons are unequally shared between the atoms in a covalent bond. So when we think of a covalent bond, what you want to think of is you want to think of like a tug of war taking place. Sometimes if you've got two atoms that are both pulling on that electron equally, you get this nonpolar covalent bond situation. So I like to think of it like a game of tug of war. So in a nonpolar covalent bond, it'd be like if you had two toddlers on either side of that bond. They're both pulling with equal strength against each other, so the electron is going to be equally shared between both atoms. So they are going to split the love that they feel from that electron. In a polar covalent bond, that's going to be where one atom is able to pull that electron closer to its own nucleus. So it's going to feel the love of the electron more than the other atom will. So this would be like HF here, and it's kind of like our H is a toddler and the F is a sumo wrestler. He's going to be able to pull that electron so much closer to his own nucleus, he's going to feel the love of the electron a lot more than that H is. So how do you know if it's going to be a nonpolar covalent bond or a polar covalent bond? What you have to look is you have to look at this chart that's down here on the next page of your notes. So go ahead and flip your notes over. This chart here is what we call the electronegativity chart. I hope you saw it first semester, but I'm guessing maybe you didn't. And the ability for you to attract an electron is how we define electronegativity. So this chart determines whether your bond is going to be polar or nonpolar. And how you figure that out is you just simply look at the numbers on the chart and do some simple subtraction. So our general rule of thumb is if the difference is between 0 to 0.4, that's going to be a nonpolar bond. If your difference is 0.5 or bigger, that means you have a polar bond. So what do we mean by that? If we think about the example on the top slide, the two examples we had were H2, which is an H stuck to an H, and HF, which is obviously our H stuck to our fluorine. So how you use these differences is you just look at the numbers. This H has an electronegativity of 2.1. This H has an electronegativity of 2.1, which means they have a difference in pull of 0. So both of these atoms are going to pull on that electron with a strength of 2.1. So this would then be a nonpolar covalent bond because the difference falls underneath 0.4. If we look at HF, for example, HF is 2.1 and F is 4.0. And when you're doing this math, you always do the bigger number minus the smaller number. So 4.0 minus 2.1 means they've got a difference of 1.9. What that tells us is that the F is going to pull the electron so much closer to itself, it's going to feel the love of that electron a lot more. So we call that a polar bond. Oh, but you can't see what I just wrote on the screen. So we're just going to go ahead and we'll write it over here. Now what that means, because the H is pulling the electron so much closer to itself, the electron is going to spend a lot more time around the F and a lot less time around the H. So because of that, what happens is this side of the atom is going to take on a kind of negative charge, and this side of the atom is going to take on a kind of positive charge because the electron is being continually pulled away from the hydrogen and towards the fluorine. So this side is getting more negative, and this side is getting more positive. So here's what I'd like you guys to do right now. I'd like you to hit pause, and I'd like you to use this chart to figure out which of these is going to be the most polar bond in each of these situations. So go ahead and hit pause and figure out which one of these is the most polar. All right, so for each of these, we gotta do just a little bit of math to figure out which one is polar and non-polar potentially. So in both these instances, our H is 2.1, and for the P in this first guy, he's also 2.1, which means our difference is 0. Again, over here, we had H as 2.1 and F as 4.0, so our difference is 1.9, so this guy is gonna be the more polar bond in that situation. If we come over here, we've got O from our chart with an electronegativity of 3.5 and the F with an electronegativity of 4.0. So that would give us a difference of 0.5. Our O still has an electronegativity of 3.5 in the second example, but now we're replacing that with an I that it's bonded to, which is 2.5. So 3.5 minus 2.5 is 1.0. So our OI is going to be the more polar bond in this situation. Over here with NO to SO, our N is 3.0, our O is 3.5, so this has a difference of 0.5 in the electronegativity, so not that big of a difference. We're here, our S and our O, our S is 2.5, our O is 3.5, so this has an electronegativity difference of 1.0, so this is going to be the more polar bond. Our last group over here is NH and SiH. N is 3.0, H is 2.1, so this is a difference of 0.9. Over here, SiH, Si is 1.8, and H is 2.1, so that's only a difference of 0.3. So in this case, the NH is going to be the more polar bond in that situation. So when you're trying to determine if a bond is polar or nonpolar, what you need to do is you need to go ahead and figure out, is our difference greater than 0.4? If it is, it means it's a polar bond, and then obviously the bigger the difference, the more polar the bond is. And we'll talk a little bit about that more in class tomorrow. So the reason we want to figure out if bonds are polar or not is because we can use them to determine if a molecule is polar or nonpolar. And this is what we're going to focus on in class tomorrow. I really want you guys to focus on identifying whether or not you can determine if a molecule is going to have polar bonds or nonpolar bonds. So I'll teach you guys this tomorrow. So for the activity, here's what I'd like you guys to do. When we're trying to figure out if we've got polar or nonpolar, the first thing we have to do is we have to draw the Lewis dot structures for all the things we're working with. So just like we've been working on in class, you can either use the picture method or the math method. So for these four guys, I'm going to go ahead and I'm going to draw the Lewis dot structures. If you feel like you're struggling with this, I would hit pause and try and do the Lewis dot structures yourself. Otherwise, you can keep following along with me in this video. So H is in column 1, it gets 1 dot. Cl is in column 7, he gets 7 dots. So in order to make the Cl octet happy, I can just share that electron between the H and the Cl. Over here, I know that oxygen is in column 6, and I know that H is in column 1, so I can go ahead and I can play connect the dots to make my O happy and my H's happy. And you'll notice I've kind of drawn it Vesper style, and that's going to be important for what we do tomorrow. CF4 is tetrahedral, so I'm going to draw him Vesper style. Oh shoot, I forgot to make that guy dotted. Whoops, let's go ahead and fix that. And then last but not least, CH3F. I've got a C here, H, H, F. All right, so here's what I'd like you guys just to do for class today. I would like you guys just to go ahead and figure out, do these things have polar bonds or not? I'm going to do these first two for you. Oh, that should be an F, not an H, my fault. I'm going to do these first two for you. I'd like you guys to go ahead and try these two. Once you've got that done, I'd like you to go to the sub, and I'd like you to get the worksheet activity. In the worksheet activity, all you're focusing on is drawing the Lewis dot, drawing the 3D structure, and figuring out if it has polar bonds or if it doesn't have polar bonds. We'll do the next part in class tomorrow. So how do we figure out if these bonds have polar, or if these molecules have polar bonds? We use that chart that's just up above the screen. So my first molecule is H and Cl. So I see H is 2.1 and I see Cl is 3.0. So I'm going to do 2.1 for my H and 3.0 for my Cl. And that tells me it's a difference of 0.9. So yes, I know I have polar bonds. We'll talk about what that means tomorrow. Down here, I have a total of 4 bonds. But it's kind of nice because they're all hooked up to the same thing. So the only things I have to look at is the difference between the C and the F. So my C is 2.5. My F is 4.0, so the difference between these things is 1.5. So what that means is each of these bonds have an electronegativity difference of 1.5. So yes, all of my bonds are polar bonds. Now what do we do if we have something like this over here, where we've got a C stuck to an H, a C stuck to an H, a C stuck to an H, and then a C stuck to an F? What we need to do is we need to look at the 2 different types of bonds. We need to look at the CH bond, and we need to look at the CF bond. So if we go back up here, I know my C is 2.5, my F is 4.0, so I can look at this bond first. So my C is 2.5, my F is 4.0, so that's going to be a difference of 1.5. So that means my CF bond is in fact polar. So now I want to look at my C to my H's. My C is 2.5. And I know over here my H is a 2.1, so that's only a difference of 0.4. So that means all these C to H bonds are nonpolar. So it is possible in one compound to have both polar and nonpolar bonds. So on your worksheet, you'll see there's a column to identify whether the bonds are polar or nonpolar. So it is possible for you to have both types in one compound. And I'll just go ahead and I'll do water with you guys here. So if we look at water, my O is 3.5. My H is 2.1, so that is a difference of 1.4. So yes, in fact, these are polar bonds. So I just like you guys to practice right now, drawing the Lewis dot, drawing the Vesper, and identifying whether the bonds are polar or nonpolar. Tomorrow, we'll finish up the set of notes talking about molecule polarity, and then you guys will have the rest of class and finish the activity. If you've got any questions, please make sure you bring them to class, because I can start by answering them for you.